Big data is difficult to classify. These are high-dimensional systems, and that means the patterns, even though they exist, are also high-dimensional and often very unfamiliar and non-intuitive. Now let's look first at regression versus classification. Regression means using existing data to predict future numerical outcomes. For example, we saw linear regression that does just that. But notice that in the case of linear regression, as is often the case, we have to have assumptions in a mathematical model, whereas our focus is going to be on classification problems. In this sense, or in classification problems, the data is slightly different. We have the observations, but each observation is in a class, and the goal is to predict the class of a new observation. So a classification problem is when each observation of the data is a member of only one of two or more categories. And the problem is that of identifying or predicting into which category a new observation belongs. So we'll talk about class 0, class 1, class 2, so on and so forth. An algorithm which can predict the class of an unlabeled data point, an observation, is known as a classifier. For example, digit recognition. This is something you probably have actually done. You draw a digit, 0 through 9, on a cell phone or something like that, and the phone recognizes your handwritten input as an actual digit. So in this case, each observation in the data is the image of a handwritten digit, and there are 10 classes, one class for each of the 9 digits. For this course, we're going to only focus on 2 classes, and we're going to focus on medium-sized but highly complex sets of data. There are a couple of reasons for this. First off, we'll also call classes positives or negatives. So we'll have, say, a class 0 or class 1, or we'll say positives or negatives. Extending to more than 2 classes is straightforward, and we'll actually do this with the digits data later on. Now the reason we focus on medium-sized is because large data means large computational times, and we can study complexity and the phenomena of big data without having massive data sets, just data sets large enough to exhibit complexity. Geometrically, in 2 or 3 dimensions, a classifier can be visualized using points in a 2 or 3 dimensional coordinate system. So what we tend to do is label the points with the class that they're in. So here we have a bunch of zeros and ones. Zeros are in the 0 class. Those points, the XY coordinates, are in the 0 class, and the 1 labeled point is in the 1 class. So can we predict the class of an unlabeled point? In this point, the case, the point shown there in red. That is the question that we want to address. Now, linearly separable in 2 dimensions means that there exists a line that separates all the class 1 points, all the points in the plane labeled class 1, from all those labeled class 0. So you can see a couple of examples here where a line splits so that the zeros are on one side and the ones are on the other. So how would we predict the class of an unlabeled observation if we have linear separation? Well, it turns out it's actually fairly simple. We can simply see which side of the line it's on, or we can find out what point it's closest to. Because if we have linear separation, then an unlabeled observation should be in the same class as its nearest neighbor, the known observation that's closest to the unlabeled observation. And when we use the closest points to classify a given point, that's known as a nearest neighbor classifier. So let's look at an example. In 1936, Ronald Fisher introduced the IRIS dataset. 50 samples in 3 classes: Iris setosa, Iris virginica, and Iris versicolor. There are 4 features: sepal length, sepal width, petal length, and petal width. So the classes are the species, and the features are the lengths and widths, respectively. Now, let's look first at a 2-class labeling for this data. So something that is in class 0 will be isetosa. So isetosa is class 0, not isetosa, the other 2, is in class 1. And we can see that the factors sepal and petal length linearly separate isetosa from the other 2 types. So we can classify as isetosa or not isetosa which species the iris is using sepal length and petal length, using a simple linearly separable classifier and nearest neighbor if classifier also. Now, if we included a 3rd factor, the petal length, then it also gives us linear separation. So notice we can rotate until we have the ability to put a hyperplane, or in this case just a plane, which is a linear object, in between the class 0 and the class 1. Now let's split the class 1 into 2 classes. So now we have the 3 classes. Not isetosa was either Iris virginica or Iris versicolor. And so therefore class 0 is isetosa, class 1 is I virginica, and class 2 is I versicolor. And you'll notice that these are not separable. So class 1 and class 2 are mixed, and if we add another variable, of course there are 4 features, but this shows with 3 features that it's not possible to separate using a plane, the class 1 from the class 2. So this means that the first type, isetosa, can be linearly separated from the other 2, but the other 2 cannot be linearly separated from each other. Now we want to only consider linearly separable data. However, there are some data sets that are clearly separable, but not linearly, that can be transformed into a different context so that we do get linear separation. So for instance, in this case, it's clear we can't draw a straight line that separates class 0 from class 1, but we could draw some kind of a curve. Now, we can't allow arbitrary curves, but we do allow transformation. So let's see if we can achieve linear separation with a transform. In this case, it's just simply representing the data in log-log space. So notice we're using log y log x coordinates, and that separates the zeros and the ones linearly in the log-log space. We might also be able to define new variables, especially if we have polynomially separable data. We can define new variables and separate it in higher dimensions. So notice that we don't have linear separability in this example, but we could separate with a parabola. In particular, the parabola z equals x plus x squared separates the class 0 from the class 1 in the zx plane. So let's define a new variable. Let's let y be equal to x squared, which gives us z equals x plus y. We can now think of each of these points not in the zx plane, but in the xy z plane. You can see here. Then clearly the polynomial separation becomes linear separation because I can put a plane in the xyz coordinate system between class 0 and class 1. So if we can transform and achieve linearly separable, then we'll accept that. but we cannot allow anything other than linear as a separator. No arbitrary curves. So suppose now we have an unlabeled point, this red dot. It's class 1 in my first arbitrary classification scheme, and it's class 0 in my second. And these are both completely arbitrary. If we can't linear separate in 2 dimensions, maybe we can separate in 3. And in general, data that's not linearly separable in m dimensions may be linearly separable in n greater than m dimensions. For example, let's look at the XOR problem. The XOR problem is not linearly separable in 2D. So what we're going to do is we're going to have 3 labeling. So 0 here is false and 1 is true. And notice that if we take 0 and 0, false and false is false. So a statement that's true and a statement that's false, the combination of the two, is false. 0 and 1 is false. 1 and 1 is true. So the only way you can get truth in the AND condition is if both x and y are true. In contrast, x or y, as long as one of them is true, then their combination with the OR is true. The XOR says that x and y being the same leads to false, and being different leads to true. Now, the AND problem is clearly separable with a straight line. And you can see all we have to do is isolate the upper right vertex labeled 1 from the 3 that are labeled 0. Similarly, the OR is linearly separable. But the XOR is not. There's no way to draw a line that separates the 1s and the 0s. However, let's define some new variables. In this case, I'm actually going to use the words true and false as the labels. And I'm going to define a new variable, x plus y mod 2. And this is going to give me a new data set. So my XOR is now, in terms of x, y, and z, 0, 0, 0 is false, 1, 0, 1 is true, 0, 1, 1 is true, and 1, 1, 0 is false. And what this does is it makes it possible to separate by going into 3 dimensions. So instead of the x, y, where I don't have linear separation, I can rotate into the x, y, z, and the 2 false conditions are at the z equals 0 level, the 2 true are at the z equals 1. So the plane, for instance, z equals a half, separates the true from the false. So when a large number of independent processes contributes to the production of a data set, then linear separation. Now let's look in terms of big data classification problems. If we have a large number of independent processes contributing to the production of a data set, then linear separation is unlikely to occur in low-dimensional contexts. For example, microarray data, we have 22,000 genes, and some are activated by the experiment in question, some are not. And when we look at that, we can see in a 2-dimensional representation of one person versus another, subject 1 versus subject 2, that class 1 and class 0 is so completely mixed together it doesn't look like there's any way possible. And indeed, we would have to embed in very high dimensional space to linearly separate. So, big data comes from complex systems. Complex systems have multiple scales. Question spanning scale require high volume with high variety and high velocity. And big data is often studied via classifiers. But big data tends to be linearly separable only in high dimensional spaces, if at all.